Put this. So welcome and hi Heidi. I started recording just that you're aware. Hi Heidi.
Hi, how are you? I'm sorry I'm late, Professor.
Not a problem, not a problem. So we have you and Anusuya, and I think we can get started. So I'm recording this session now, just that everybody can review this video now. So, okay. So the idea is now to essentially first talk through the open questions. So Anusuya, I want to go with your question first. So you had a question about an independent sample t-test, correct? So I'm not sure your microphone is working, but I hope you can see my screen. So we talked about an independent sample t-test in your discussion board entry, right? So you essentially go for an independent sample t-test. You go in SPSS, and I hope you all can see it. If in case not, please raise your hand. So you go on compare means, you go on independent samples t-test, and you choose weight of the child as a function of the grouping variable, which is your smoking yes, no. And as you can see, this is coded as either a 1 or a 0. So if you define the groups now, and this is what I suggested as a troubleshoot point for you to define the groups, and you define them in either 0 and 1. So if you define these groups and you click OK, then your analysis should actually work without any problems, just like indicated in the 2-sample t-test Word document that is posted on the weekly materials. Did this work out for you, Anusuya?
So when I tried it again, can I like walk you through the steps that I did to get there?
Sure.
Okay.
Did you just for my understanding, did you follow the outline on the document with the instructions?
Yeah, so I looked at the last page where it had it was the ounces, and it was comparing the ounces of the baby. I think it was the ounces compared to smoking. Yeah. That was the one, not that one. I think it was like further down.
Yeah, it's further down now.
Yeah. So I used that one. So I did the analyze, compare means, independent t-sample. I also made sure that in the third one where it says the smoking 0 and 1, I checked that off. But when I went to run my test after that, and even here, because when it didn't work the first couple of times, I even like right-clicked on the smoking one just to see like what the variables meant. And I thought that like the 0 and the 1, I tried to like use the data select cases to like make a new data set, but like that didn't work, like another filter. That didn't work as well. But I did the analyze, compare means, independent t-test, and I entered a 0 and the 1. I don't think I touched anything in the options. I think it was 95%. I just left it at that because that was the question. But when I ran it, it would only give me the data for people who smoke and not and it wouldn't show up anything. Like it would set n was equal to 0 for the people who did not smoke.
Yes, so you did not, so your problem specifically is not here with analyze, compare means, independent sample t-test. So that what I just did, you are able to reproduce, correct?
Yeah.
Okay, so that worked.
Yeah. So even, I think I tried, no, I don't think I tried to reproduce it with the weight. I think I went straight for the age.
Okay. So what is the research question that you're meaning to ask?
So when I was doing everything and I went there, I went to the analyze, compare means, independent t-sample. Yeah.
Yeah. So
I went
what
there.
do you mean? What do you mean to compare?
So I was comparing for the test valuable, I put age of mother.
Yeah.
And then for grouping variable, I put smoking. And then I put smoking during, clicked on define groups.
Yeah.
Group 1 was 0. Group
Mhm.
2 was 1.
Mhm.
Then I continued. And for options, I'm pretty sure, yeah, options I left that as like, as it was.
Yeah.
Yeah, it was the first one. Yes. And then I clicked OK.
Yeah. So you're
Yeah,
not getting this.
no, when I ran it, it wouldn't show me like, it would show mother who did smoke and it would show the 114 and all of that at the bottom. It would show me that. But for N, for the mother who did not smoke, it would show N0.
Okay.
Or I don't remember if it was N0 or NA, something like, I think it was NA.
Okay. Then did you select any cases? Did you go on data and select cases?
Yeah, so I tried to do that again. So then I did that and I did smoke during pregnancy.
So when you ran
First I
that,
clicked if condition is satisfied.
yeah.
So I
So
clicked on.
so the trick is, I think this is what's happening.
Okay.
You subset, so you selected the condition. So you said, if the premature weight or the smoking, or you probably have now the smoking to some extent subsetted, just as a potential reason why that is not working. If you're saying mother that smoked or not smoked, whatever. So you basically, if you select the criterion, it does not analyze those cases where this is actually true, or where's the smoking now. So if this is the case, then this will give you.
So it basically got reversed. So like.
Yeah. So you need to reverse this. So if I do now this analysis, I get the same thing, right?
Yes. Okay. Okay. That
Yeah.
was coming up.
Oh, no. Okay. But we reproduced it. Now your problem, right? Okay. So now go on data, go and select cases, and make sure that you selected all cases, because if you are excluding those that smoked or not smoked, you will not have these in the analysis. So you need to set this filter off, and now you have both groups again represented in your data set.
Oh my God, that makes sense. Okay, thank you.
You're welcome. So I think this is the reason.
Yes.
Please confirm it and let me know whether this was the reason, because now if you do this analysis now, you get both groups represented again in your data.
Oh my God, that makes so much sense now. Thank you.
Okay, you're welcome. Okay, glad that we resolved this. So, okay, any other questions, Anusaya?
No, that was like, I went through everything else. Everything else was perfectly fine. It was like the last questions.
Okay, no, that's I'm happy to hear that. Okay, great. If any other questions, let me know. Heidi, your turn.
I think I was grappling with something similar as Anusaya.
Yeah.
But I haven't done the test yet. So I was just on the homework on the labs. And I was having a problem making N equals 707. N was always was turning into 800. And I did that sort of organization that you just went through, which is I chose all cases, but it was still giving me like 800 of the cases instead of 707. And I'm not sure, I'm not as erudite, or I can't explain it as well as Anusaya did, sorry.
Right.
But I think I did something similar incorrectly.
Okay, so let's go through this slowly. And I think this is why this is good, this review sessions. And that's why I want to do the troubleshooting, because sometimes these statistical software can be a little complicated, particularly when you work the first time with them. So in principle, you have always all cases selected. All cases will be represented in your data set. That means if you want to subset your data and you just want to analyze a subset, You can do that easily. So a premature birth. So you go on data, you go on select cases. And here you have essentially, you have several possible options that you can employ. The easiest one is, so all cases is always all rows, all case entries. If you go on if condition is satisfied and you go on if, so here you can actually define what you're interested in. So if you delete this and you're selecting, what was it, what we're subsetting, I forget, premature birth.
Yeah, with the preemies. Yeah, the preemies.
Okay, the preemies. Okay, good. So we have premature weight, premature babies. And if you set this equal, and if you look here, essentially you have ones and zero. I can't even scroll. Okay. And if you do premature birth equals 0, you get a subset of only those where this is not correct. Meaning, and now on equal, it will scratch out all which were premature. So 1 fulfills the criterion as being premature. As such, it will exclude those that are premature. So now you have an analysis. Now you have the capabilities to analyze only those that are not premature. And if you now go on the frequency overview or the crossstep or whatever you want to do, if you want to now define the premature is now obviously not really meaningful, but if you want to now have all low birth weights within your group of premature babies, you basically can only, you're looking now at a subset that were not premature. So these are the 707. The trick now, and this is what happens to your colleague, Anusaya, and please excuse if I mispronounce your name. You basically, once you want to go back to your overall analysis of the entire data set, you need to take this criterion off again, and you need to select all cases. And that is important to do, because now you can look at the premature, now you can reproduce the descriptive statistics. Now you go back to frequencies. Now you look at all the low birth weights, but now you're looking at 800. Does that address your concern, Heidi?
Yes, I think it does. Thank you very much. I wasn't allowing for the 0 after preemie. I think that was probably the mistake.
Yes, and this is the tricky thing. So a cleaner way would be to kind of create a new data set. And so I'm coming now from the R world, and R you would create a subset data set and a separate object, so to say. So that's a little bit easier to keep an overview. But in SPSS, you can, with select cases, you can do the subset analyses, and that essentially allows you to look at just a subset of your data. But it's, you got to keep an overview if the filter is off or the filter is on. So that's just really important and central. Okay, any other questions, Heidi?
None for me, thank you.
None for you, okay. So another colleague joined. Hi, welcome.
Hi, hello.
Hi, so I forget your name.
My name is Cece. Everybody calls me Cece.
Cece, good.
Yes.
Okay, so Cece, do you have any specific questions that I can answer? SPSS
no,
really.
Actually,
No?
this week I was pretty comfortable, so I'm good this week. I'm just
Okay,
dropped in to see if there's anything else going on.
Okay, sounds good. No, well, so we can. So you have pretty clear instructions on the SPSS exercises. So if you're comfortable, then I think we can go. Did you try to solve the t-test exercises and the solutions? Are there any? Is there anything I can explain with those exercises, maybe?
Would you mind going through one for us, walking us through one?
Yes.
Thank
Yes.
you.
So when you want to do a one sample t-test, Okay, so this is the first example of the PowerPoint. So you essentially have a one sample t-test. That means you're using a t-distribution. And this is already where one of those aspects starts, t-test and our t-score table. So you have, last time we talked about the z-score table, right? So now for this class, it's actually a t-score table, which is slightly different. And sorry, I'm just going to find the table. Distribution table, see it there. Oh, it's coming up. Okay, so the t-distribution table is different to look at as compared to the z-score table. So in the t-distribution table, you are going by the degrees of freedom, correct? So you will need to find the t-score that you essentially are being interested in. And that is different from the sample size that we used for the z-score. So the degrees of freedom essentially are always n-1. So that's your variable, that's your n-1. And that essentially gets you to your degrees of freedom. The reason for that is everything evolves around the sum of squares, meaning that when you are calculating the sum of squares, and you remember from the standard deviation, from the calculation of the standard deviation, you essentially you calculate your deviations by subtracting your individual score from the mean of your variable. That gives you the deviation from your mean, from the center. You're squaring these deviations and you're summing all the squared deviations up, bringing you to the so-called sum of squares. And the concept of the degree of freedom is that you only take those entries that are needed to evaluate this sum of square, meaning that when you have the sum of squares given, you do not need one entry. That means you only need those entries in the variable minus one of these entries to derive that missing entry, that one entry that you're not taking into account from the sum of squares, because it's basically a sum of squares minus all the other entries gives you that last entry. And this relationship is reflected by the degrees of freedom. It's actually you're dropping one for the purpose of resembling a normal distribution in more detail. And you're aiming to represent this by correcting it for that one entry. And it's conceptually a little hard to grasp, but it's essentially you are by that meaning to resemble the normal distribution shape in more accuracy. So the idea here is that when you have a sample of 10 babies, your degrees of freedom is n-1, meaning it's 9. So when you are here, so the question you're facing is the statement of a problem. Do SIDS babies have lower birth weights than other babies? So the mean birth weight of non-SIDS babies is 3,300. When you're taking now a sample of n equals 10 or a degree of freedom of 9, you calculate that sample mean with 2,890.5 with a standard deviation of 720, which is the next distinction between a t-distribution and a t-test and a set distribution. For the set distribution, you need to know the standard deviation from your population. So this is given for a set test. For a t-test, you're estimating your standard deviation from your sample. So now what you're trying to do on this, in this example, you're trying to quantify, and I'm opening an Excel spreadsheet because then it gets easier to kind of illustrate that. So you want to quantify now your 95% confidence interval. So what is the 95% confidence interval for the true mean, mu, based on your statistics? So again, as a recap, the 95% confidence interval is that interval within which, around that sample mean, you're confident the true population mean is located, meaning you're comparing it to a true population mean of 3,300. So you have now 2890.5 as the mean of your sample. You're building a standard with a standard deviation of 720. You are now calculating the standard error of the mean. Again, as we discussed last in the last review session, the standard error of the mean is essentially a reflection of the variability of hypothetically drawn repeated samples. So you're drawing repeated samples, and you get now different means. And we're assuming that sample mean that you have at hand, this is the mean of all your means. That's the mean of means. That's the only mean you're interested in. But all the other samples that you have drawn, these hypothetically assumed samples, essentially distribute around this mean of means with a certain variability. And this variability is going to be less than the standard deviation of the population, because it is actually only the distribution of the sample means. So that when it becomes the sampling distribution. So it's the distribution of the sample means around our sample mean that we have given. So the idea behind that is, if we are now looking at 2890.5 with a standard deviation, this is our sample mean, X bar. This is our standard deviation of the sample of 720. We have an N of 10. N is 10. So we're calculating now the standard error of the mean. And our standard error of the mean is essentially nothing else but the standard deviation of our sample divided by the square root. Well, I'm zooming in a bit. More. Is the square root of our sample size, which is 10. So we get a standard error of the mean of 227.7. So now, what becomes now the next interest is exactly this formula. Right? Let's take this. So we want, I'm just reproducing, I'm walking you through the calculation. So you have the calculation right there, right? I just want to illustrate the calculation and why this presents that way. So you want to have your T statistic now. And your T statistic is basically determined by the X bar, which we have here, and the mu, which is 3,300. So now we are looking at an X bar minus the 3,300, which is now our difference. That's exactly 2890 minus 3,300, which is 409.5 negative, so minus 409.5. So now to calculate the t-score, you essentially take this minus 409 and you divide it by the standard error of the mean. And that gives you minus 1.7985, minus 1.8. So now if you want to build your 95% confidence interval, you remember for the set distribution, you are looking at 1.96. And if you had a sample that is greater than 500, you are essentially looking at equals 500. You're looking at 1.96. So again, the way you're reading this t-test, the way you're reading this t-test, so you can do this with a one-tailed analysis, which we don't have. We have a two-tailed analysis. 99% of all analysis will ask for a two-tailed analysis. So you essentially, you look for your critical value. You're basically defining that alpha, that rest risk of a type 1 error that you're willing to accept. So you have here from 20, 10, you have 0.05, 0.02, 0.01. We are looking for 95% confidence interval, which essentially the 95% is that confidence that was in that interval was in which you 95% confidence you have located the true population mean. So your confidence interval is essentially 1 minus your alpha. So your alpha is 5%. So now to determine which t-score will basically allow you to determine this interval, you need to define your degrees of freedom, which we came to determine as 9. So the t-score, the critical value is 2.26. So that's the critical t. It's 2.26. So with a t of minus 1.8, do you think this is gonna be significantly different or not? Because you can say this already here, so you can assume already that your p is likely gonna be greater. So essentially, what you are doing now is you're using this critical t to determine with the standard error of the mean what your confidence interval is. We have a mean of 2890, and with the mean of 2890, you can define now the lower limit and the upper limit of your confidence interval. And your lower limit will be the 2.26 multiplied by your standard error of the mean. It's the mean, this x bar minus that t, that critical t, multiplied by the standard error of the mean. So in the same fashion, you will calculate now your x bar plus 2.26 multiplied by the standard error of the mean. That gets you essentially the upper limit. So you know now that your sample mean essentially is with 95% CI is now, and this is how you would express this in a publication. You say it's 2890.5 with a 95% CI from 2376 to 3405. So when comparing this now to the mu, you know that there's no significant difference. And this is also what you would conclude by just comparing this to your critical t. And this is this calculation that essentially happens here. So the two-tailed test is here 0.1054. So if you are going now down to 1.8, you will find 1.8 essentially not calculated. Well, you could calculate it obviously, but essentially you are getting here a p-value of 0.10. So this is not significantly different because the p-value is greater than 5%. But when you have the confidence interval, would essentially be located here. So this is 0.527. This calculated value, if you would calculate it now with software, you would essentially get a two-tailed 5.3% on each side. So your confidence interval is essentially wider and does essentially capture the population mean. Therefore, you know it's contained within that range, and it will not be significantly different because your confidence interval is determined by 1 minus alpha. So this is how you can essentially, this is where the intersection between hypothesis testing and the confidence interval is essentially located. So you basically, you can hypothetically, you can use confidence intervals to do hypothesis testing, but you should always do a formula analysis. Does this help somewhat with this example? Was this clear how you determine essentially standard error of the mean? You determine the critical t. It comes from the t table, where essentially you look for a 5% two-tailed p-value. This is your alpha in a two-tailed test. And this is how you determine that. And this is how you would also do it for the other examples. Does that make it clear and explain the calculations?
Yes, that was clear.
Yeah, all right. Happy to hear that. Do you want to do another example, or do you want to talk about something else? Anything from the lectures you're interested in?
I could go for another example if you don't mind.
No, absolutely.
This
not.
is very
Absolutely.
helpful to me. I'm a very like sort of auditory kind of visual person at the same
Yeah.
time. So thank you.
Okay. No, of course. No, it's I believe in hands-on, and it's I believe in hands-on statistics, to be honest. And it is definitely easy, and it's great that you have these examples here. But I think it makes sense that somebody walks you through the steps. So I think this is a good exercise, because it kind of illustrates what the dynamic is, how you really calculate it. So absolutely, let's do another one. Okay, same example. We have now systolic blood pressure was measured for 15. So we have now 50. We have a sample of 15 individuals. So again, so we have, wait, hold on. So now this is a little different. So we have now a paired sample. We have now the mean difference is, this is second. So now it becomes a little different, because now we have a mean difference. So we have a mean difference of minus 5.3. So they had a decrease in the blood pressure. The standard deviation of this difference was 12.8 millimeter Hg. Oh, no, okay, so SD is 12.8. So this means that basically you had these 15 individuals. They were measured at the first year, and then at the second year again, or 4 years later, and they had a decrease in their blood pressure. So you had 15 entries. You had year 1 and year 2. The way you're calculating this in a PRT test, you would essentially build the difference and then determine again. So you determine your alpha. So your alpha is again 0.05. And now essentially you're doing essentially the same thing. So now the first thing you need to define is, what is your null hypothesis? You remember, null hypotheses are always defined as that there's no difference between your population, or no difference to 0, right? If you want to know whether there was a significant decrease, if that decrease of 5.3 millimeter Hg was significant, you would need to compare it to what you're interested in. You need to compare it to 0, because that would imply that there was no change. Whereas your alternative hypothesis is that there was a change that was greater than 0 at an alpha of 0.05. So now this time around, you do nothing else, but you're subtracting your mean difference from the mu, and the mu in your case here is that 0. So essentially you have minus 5.3 is this numerator, whereas the denominator is again nothing else but your standard error of the mean, which is again calculated as standard deviation divided by square root of the n, which is 15. Oops. Oh, okay. So your standard error of the mean is essentially 3.3. So again, degrees of freedom, we have 15 individuals that were measured. Degrees of freedom minus 1 is 14. 14 at a p-value of 14 is 2.14. So that critically, so that alpha, let's move this up here. The alpha was the critical t value is now 2.14. So now you want to have your lower limit and your upper limit. Your lower limit is once again 2.14 multiplied by the standard error of the mean, and the mean minus. So this is minus 12. So now we have the mean plus the critical value multiplied by the standard error of the mean. It's 1.772. So once again, we know now that the difference is minus 5.3, 95%, 95% CI from minus 12.4 to 1.8. So now the is different. Look at this. No. Really? Okay. Difference. Okay. Let's look at this. So let's see, minus 5.3, 95% CI is minus 12.3, 12.4 to 1.8. So this is how you would describe that. So you know already by the naked eye, you know already that this will not be significantly different from 1 year to year number 4, because it is containing the zero. So again, you are assuming that your null hypothesis is that the mean difference is essentially 0. That's your null hypothesis, and you're rejecting this if your p-value is smaller than 5%. So you're rejecting if you have a t, or if your t is smaller than 2.15. So again, you're calculating now your oh, it's not even showing the 90% here. Okay, so this is basically your 95% CI, and you see already here by the naked eye that it does not contain your it does contain your 0. So that means by definition, if it wouldn't contain the 0, then you can say, okay, so if both upper limit and lower limit are negative, to have a negative sign, you can a priori reject the null hypothesis, because your 95% confidence interval was built with the critical value. So that implies and contains already the information of the 5% alpha that you're willing to accept. If you are calculating now the actual t, so the t is being calculated as the minus 5.3 divided by our standard error of the mean. And this is here 1.604. So this does not this does not exceed the critical value of 2.14. So does that make it clear? So that's a paired sample t-test. The independent sample t-test is a little bit trickier, because the independent sample t-test essentially requires you to calculate a pooled standard error of the mean. And that's over a pooled variance. We can do the calculation if you're interested in it, because it will essentially, particularly here with unequal variances, you get to that point, you're basically aliquoting the number of individual in each group. So here they're the same size, both samples are the same size. We have 15 and 15, so that makes it a little easier, because this number essentially here will change if there are different sample sizes, and so kind of you're aliquoting them to the size of each population, or of each sample population. Here you have different standard deviations for each group. So these you derive from here, and you're creating here a pooled variance. And this pooled variance essentially comes into effect here, where you're pulling it together, and you're basically including it here in your t-score calculations. But again, the same principle applies, where basically you are determining your degrees of freedom. And the degrees of freedom now, you remember how I said you can once you have the sum of squares for each variable, you can drop one entry from your variable, because you have the sum of squares, you know this sum of the squared deviations, and you can't drop 1 because you can derive that missing value from the sum of squares. And so you're dropping this for each of your variables. So you're dropping this from your population sample, from your sample population 1, and you're dropping this also from your sample population 2. So this essentially gives you a degree of freedom of n-1, n-2, minus the 2 that you can drop from each of your samples. This puts it a little bit of difference, and this is why it's important to understand the difference between a paired sample t-test and independent sample t-test, because you remember, for the paired sample t-test, your degrees of freedom are here determined by the number of differences, because you're building differences for each of your individuals from one time point to another. So the paired sample t-test always has a pairing within an individual that essentially is most of the time somewhat chronologically related, meaning you have a before and after, or a year 1, year 4 assessment. So the degrees of freedom are only n-1. So that's certainly important for the quiz and the exam to keep in mind. So with the independent sample t-test, it's slightly different because the hypothesis is a different one. So essentially, when you build your distribution of the sample means, when you have your mean difference for your sample, you essentially assume this to be the mean of the sample differences within your before and after assessment, but the sample is the difference. So here it becomes different because the assumption, the conceptual framework here for a t-test is, and this is why it's important that you have independent standard deviations at independent sample sizes, because the idea is that you're drawing now a random sample from population 1, random sample from population 2, you're subtracting the means from these two, and you're throwing them back in the pool, and you just keep that mean difference, that one difference from that random sample, you put that in the pool. Now you take another sample, different random sample from sample population 1, different random sample from sample population 2. You again build the difference, you get another mean difference. You drop that in the pool, and the rest goes back in the sample. So you're drawing this repeatedly. By that, you get a difference again. This is this difference between x bar 1 and x bar 2. And you assume this to be the mean of these random samples that you have drawn. And you have, again, you have one difference, which is the mean of your mean differences. And then you have this variability around it, which is reflected by the standard error of the mean. But the standard error of the mean this time incorporates the variance of both samples. And that is important to keep in mind. And this is the main difference. And this is why you need to treat them independently. And this is why you determine the degrees of freedom independently. And this is why you have a degree of freedom that is independent from each other. Does that make sense? I know independent sample t-test is a little tougher to quiz.
So this is the independent sample of the t-test that you just explained, correct?
Correct. This
Okay.
is independent sample t-test. And
Thank
this is the concept behind it. And you will, for example, you will see when it asks you, and I think SPSS does this as well. So there are different approaches. So it will ask you in Excel, for example, you do t-test. T-test. If you go here in the formula builder, so it will ask you for t-test. Was it? Yeah. It will ask you here type. It will ask you here this tails. It asks you for the number of tails. So you say 2 tails, and here it will ask you whether. Okay, so here down, sorry, this is small, but you basically say t-test paired with 1, right? Degrees of freedom is the difference. So you will give it before and after. That was not well shown. So let's assume you have here a before and after. And then you have array 2, that's the after, right? So now, okay, I wasn't really prepared to show that, but you have, okay, tails is 2 tail test. And here with type, it will ask you, okay, do you have a paired test? If you say yes, it will treat that with one degree of freedom, which is basically just the number of differences, which would be here in the third column, which is essentially this minus this, or this minus this, essentially. So you have these differences are determining the degrees of freedom, and this is why it's important that you define this for a t-test. Then you have a 2-sample t-test, which is homoscedastic. Homoscedasticity means that there's equal variance between the groups. And we have seen here why that is important, right? Because you have a different formula, right? If this is homoscedastic and the variance is the same for both groups, you can treat this arithmetically different. If you have 2 samples with an unequal variance, you know that you have to take this into account and you have to calculate this pooled variance. It's actually also labeled a Welch's test. It's a special form of a t-test. But this is important. You're treating these two independently and you're deriving this difference of the variability and the variance of this difference independently. So this is why you need to treat this separately. Okay, so standard error, yeah. So this is the formula for the standard error. You basically have you have the standard deviations from both of these samples. You divide them again by the sample size, just in the same fashion, and this gives you this pooled standard error. And then essentially, you have the difference between both samples. You divide it by the standard error. This pooled standard error of both samples gives you a t-score here for this example of minus 2.92, which you know is exceeding with a sample size of 28. You have here with a 2-tailed hypothesis at critical value of 2.05, which is clearly exceeded here by minus 2.92. So this is how you would approach this. So I hope that makes things a little clearer. Okay, any other questions?
Not for me. Thank you so much for going through that. I really appreciate it.
Of course, my pleasure. As I said, I really want to do this every week. Next week, I would need to do it a little earlier. Are you available earlier than 8 p.m.?
Yes, actually, I prefer earlier than 8 p.m.
Okay, so that's great.
Earlier is fine.
Yeah.
Earlier.
Yeah, would work for you too. How about we do something like noonish?
I can do that. Noon?
Yeah.
Noon is fine.
Noon is fine. Perfect. Yeah. For you too? Anus. Perfect. All right, good. Then let's do next week at noon. And let's go through week 5 the next week. Okay, great. As for the rest, good luck on the quiz. Please post questions to the discussion board if more questions. And I don't know, I can post a video, I can give some explanation where the discussion board, post screenshots or whatever works. We'll figure this out.
That's great. Thank you so much.
Thank you.
Thank you. Thank you. All right. Have a good night now.
Bye-bye.
Bye.
Bye.